Okay, so we've got this problem right here, this non-homogeneous problem, and then plus the homogeneous boundary conditions. We're going to look at something specific in a moment. The general framework is the following. We have this equation, and we want to come up with some function called the Green's function, such that this is true. So we look at the integral from y equals 0 to 1. In general, it would be y equals a to b. Let me actually do that now. Y equals a to b f of y times g of xy dy. So you want to find some Green's function that satisfies this. In the previous video, we saw that if lambda equals 0 is not an eigenvalue, so if 0 is not an eigenvalue, then we can write g as an expansion of we can write it as an eigenfunction expansion, phi k of x, phi k of y over lambda k, with a minus sign in there somewhere. But now what we want to do is we want to get an explicit formula for g of xy. And we're going to do it in the following way. Let's imagine that f of x is equal to delta of x minus x naught, where x naught is some point between a and b, some number between a and b. Then what changes down here? Well, f of y is going to be delta of y minus x naught. And now, when we do this integral, g, we have the delta, we're just going to evaluate g where the variable of integration y is equal to x naught. So this is going to be equal to g of x, x naught. So in other words, what we have here, g of x, x naught, this is going to be a solution to this differential equation with these homogeneous boundary conditions. Okay, so in other words, g, if we change to so g is going to be a solution to this differential equation with these homogeneous boundary conditions. So now if we want to compute g, we just solve this differential equation with these homogeneous boundary conditions. Okay, so let's look at a specific situation. Let's look at a situation where we have phi double prime is equal to f of x, and we know phi of 0 equals phi of 1, and they're both equal to 0. Now, you've solved second order non-homogeneous equations before in your differential equations class, but typically those were initial value problems. So in other words, you knew what phi of 0, you knew what phi prime of 0 was, and then you wanted to solve this equation. But this is different. It's a boundary value problem. So we're going to look at Green's function as one way of solving this differential equation. Okay, so here's what we're going to do for this problem. The Green's function is going to satisfy phi double prime. The Green's function is going to satisfy this differential equation with the Dirac delta function here. So in other words, it's going to solve g double prime, or let me be more explicit here. The second derivative in the x variable. This is going to be equal to the delta of x minus y. And then we also want g to satisfy these same homogeneous boundary conditions. So g of 0y is equal to g of 1y, and that's equal to 0. There are also two other properties that g is going to satisfy, or that g does satisfy, that we will get to in the course of solving this problem. So we want to find our Green's function g, and we're going to start with this fact here. So the second derivative of g in the x variable is equal to 0 when x is less than y, and is also equal to 0 when x is bigger than y. So if you look at an interval that does not contain y, if we look at an x interval that does not contain y, then g double prime, I'm going to write it right here, g double prime of xy is equal to 0. And the prime notation here, because I don't want to keep using the Leibniz notation here, the prime notation refers to differentiation in the first argument, in the x argument. Okay, so this is true if x is less than y or if x is greater than y. So in other words, this tells us that g of xy, its second derivative is equal to 0, so it's equal to ax plus b when x is less than y. and then it's equal to cx plus d when x is greater than y. Okay, there's clearly some sort of discontinuity happening when x is equal to y. So across x equals y, we don't know that g of xy has this form ax plus b and cx plus d, but we do know if x is less than y, where the delta doesn't take effect, then we've got g of xy is equal to ax plus b, and when x is greater than y, g of xy is equal to cx plus d. Okay, so I want to find my coefficients a, b, c, and d. Those are 4 unknowns, so I basically need 4 equations. Now, the boundary conditions give me 2 equations. So if I look at x is equal to 0, I'm going to get 0 is equal to g of 0y. Well, y is always going to be bigger than 0 and less than 1, or bigger than the left endpoint and smaller than the right endpoint. So g of 0y, I'm going to be at this formula here. If you plug in x is equal to 0, you just get 0, so this is b. In other words, this tells me b is equal to 0. So I'm going to record that simply by erasing that. I'll be doing that throughout this problem. I'll be modifying this as we get more information about the coefficients. Similarly, 0 is equal to g of 1y. If you plug in 1 here, 1 is bigger than y because y is bigger than 0, less than 1. This is going to be c plus d. In other words, d equals minus c. D equals minus c. So you can write this as c times x minus 1. Okay, so I've used these 2 boundary conditions. Well, I need 2 other equations, basically, to figure out what a and c are. The first I'm going to use is that g is continuous. So this is one condition. The next condition that I know about g is continuous. Why is g continuous? If g had a jump discontinuity, the derivative of g at that jump discontinuity would be a Dirac delta function. In fact, this is one way you can define the Dirac delta function or Dirac delta distribution. If you have a jump discontinuity of height 1, so it's like 1 here and 2 here, then the derivative of the function at that point is going to be the Dirac delta distribution. If you have a jump discontinuity of height 5, so let's say 1 here and 6 here, then it's going to be 5 times the Dirac delta function. Okay, so the derivative, if g had a point of discontinuity, the derivative of g at that point would be equal to the Dirac delta function, and its second derivative would be more singular than the Dirac delta function. So the derivative of the Dirac delta function is not equal to the Dirac delta function. But here we're assuming the second derivative is a Dirac delta. So in other words, g has to be continuous. If g was not continuous, there's no way its second derivative could be equal to a Dirac. So g has to be continuous. So how we use that over here is that it's got to be continuous, in particular when x is equal to y. So in other words, this tells us that ay has to be equal to c times y minus 1. Ay has to be equal to c times y minus 1. In other words, a is equal to c times y minus 1 over y. So I'm going to record that over here. So a is equal to c times y minus 1 over y, and then we're going to multiply that by x. Okay, so I'm going to erase these. I need one more equation to help me figure out what c is. And for that, I'm actually going to go back to the differential equation here. I'm going to do a step here that if you go back, it's like, in some sense, completely unrelated. But if you go back to when we derived the Rankine-Hugoniot condition, we were integrating over discontinuity, or like something weird. We're going to be doing that here as well. We're going to be integrating over a discontinuity in the derivative. And if you look back at that, it'll make some of this make a little more, it'll make what I'm about to do a little more rigorous if you have a problem with it. But I'm going to integrate this from y minus epsilon to y plus epsilon. And I've got delta of x minus y dx. Now I'm integrating over y, like y is in this interval, so I know this is equal to 1. And since the Dirac delta function, I've got y minus epsilon to y plus epsilon, the Dirac delta function is equal to g double prime of x, y dx. And so bringing the 1 down, I've got 1 is equal to, Okay, now I can use the fundamental theorem of calculus over there. This is the point where you might have, it might be a little uncomfortable for you. We're going to apply the fundamental theorem of calculus over here. We're going to get g prime of y plus epsilon, comma x, minus g prime of y minus epsilon, comma x. Now really, we kind of need to break this into y minus epsilon up to y, and then y to y plus epsilon, and kind of handle it that way. But you're going to end up with the same thing. Okay, so g prime of y plus epsilon. Well, this is x. Y plus epsilon is bigger than y, so we're in this formula here. The derivative of that with respect to x is c. So we're going to have c here minus, when I take the derivative here, what do you get? Well, you get c times y minus 1 over y. And if you get a common denominator over here, this is equal to c over y. In other words, c is equal to y. So I'm going to replace this c with a y. Okay, and if c is equal to y, this is y over y, which is just 1, so this is y minus 1 times x. So this is the Green's function. Okay, so I'm going to erase all of this. So what this tells us is the following. The solution to this problem here is phi of x is equal to the integral y going from 0 to 1 f of y g of x y dy. This marker is now good. Sorry, that was probably loud in the microphone and a little annoying. Okay, where g of xy is given by this function here. So in particular, I think, in the homework, I might ask you to do something like this. And x here, if that was the case, then we would have a y here. This integral gets split into two integrals. One from y going from 0 to x, you're going to be in this. And one y going from x to 1, you're going to use this function here, or that branch there. Let me just point out now, if we want to do this the eigenfunction expansion way, what we're going to get is the following. We're going to have the sum k equals 1 to infinity. We need to be a little bit careful. So we know kind of the natural eigenfunctions for this are going to be sine of k pi x. But we need to normalize these so that if you square them and do the integral, it equals 1. So really, we're going to use, if we want to think about eigenfunction expansion. These are just like you would ordinarily only do one of them. I'm just showing how these relate. So phi k of x is equal to the square root of 2 times sine of k pi x. And that's just so that the integral from 0 to 1 of phi k squared is equal to 1. Okay, remember before we did 2 times phi k squared, but if you square this, you get the 2, and then you get sine squared, so everything works out properly. But for the formula to work, we need the sine functions, or the phi k's, to be L2 normalized, meaning if you square them and do the integral from 0 to 1, it's equal to 1. Okay, so this is going to be equal to phi k of x times phi k of y, so it'll be 2 times sine of k pi x sine of k pi y divided by minus the corresponding eigenvalue. So I'm going to put the minus sign out here. And the eigenvalue is k pi squared. So in other words, this function here is equal to this function here. Graph it in Desmos and you'll see that this is equal to that. Okay, why do we know they're equal? Well, graph it in Desmos and you'll see. But mathematically, we know, I haven't proven this, but we know that Green's function is unique. We know this is one way to write Green's function, and this is another way to write Green's function, so they have to be equal to each other. Which obviously, it's not clear to me that these two things should be equal to each other, but they are. Okay, so which is kind of interesting, which is kind of an interesting thing by itself, if you ask me. Okay, so that's it for this video. In the next video, we're going to look at a problem where the left-hand side is a little more challenging, and the right-hand side is also going to be a little more interesting as well. Okay, but that's it for this video.